So in last class, I left you an exercise that I will be using today. So remember, we have this martingale, and it's uniformly bounded in L2. Then I've shown that you can find x in L2 such that xn is converging to x in L2, and I claim that xn it's equal to the conditional expectation of x given fn. Okay, so this I proved, this I left to you, but so let me prove it. So I want to show this identity. So by conditional expectation, if you want to prove that some random variable is the conditional expectation, what do you need to prove? You need to prove that this random variable belongs to fn. Okay, but this is by definition. And then you have to show that they integrate equally on fn. So you have to prove that for any a in fn, a xn dp, it's equal to a x dp. Right? So this is the second condition. And why this is correct? Well, you know that xk is converging to x in L2. So you know that a x dp it's equal to the limit k of a xk dp. On the other hand, since a belongs to fn and xn and xk it's a martingale, you know that the conditional expectation of xk given fn it's equal to xk. You prove that, you know that by definition for k equal to n plus 1, and then you iterate that to get it for any k larger than n. And since this is true, xn. And since this is true, this means that xk and xn integrated on the set fn, the same set. So this means that if k it's larger than n and a belongs to fn, xn dp it's equal to axk dp. Okay, and therefore this sequence it's constant for k larger than n. It's equal to the integral of xn over a, and therefore we have our identity. Okay, questions about that? Okay, so not only, so if we have a martingale which is bounded in this sense in L2, you can find x in L2 for which xn is converged to x in L2, and moreover the martingale xn is just the conditional expectation of x. Okay. So we have a pretty clear understanding of what's a martingale bounded in L2, and we want to extend that to LP. Okay, so the first theorem of today will be to say that, well, let's assume that p is larger than 1 and that xn it's the martingale you obtain by taking the conditional expectation of x given fn. So you fix x in LP. You consider that martingale, and my claim is that xn converge to x in LP. Right?
So the union of the sigma algebras.
That's a good point. I will be, so as he mentioned, I'll be assuming, so remember that we have a probability space, omega fp, where these martingales, these variables are all defined, and we have a filtration fn. And I assumed that these filtrations are all contained in F. Okay, so filtration, remember, it's a sequence of sigma algebra which is increasing. And to make everything, to give a sense to everything, I'm assuming that these Fn are contained in F. Actually, I will assume that F, in order to prove this theorem, and I don't lose any generality if I assume that this sigma algebra F, it's actually the smallest one which contains all these Fn. Okay. If it's larger, you just consider this one which is smaller, and you take your variable x, and you take its conditional expectation with respect to that, and you get a new one which is F measurable. Okay. So without saying, from now on, I will be always assuming this property. All right? Okay, so let's prove this theorem. I will first assume that x is bounded. So that x belongs to L infinity. Okay. So if it belongs to L infinity, it belongs to L2. And in L, so this means that the supremum in n of xn squared is finite. Right? X is in L2, so we know that this is increasing, it's bounded. Well, okay. So this is x. I'm defining xn by this object, right? I'm assuming that x is bounded. I'm defining xn by that. And, well, xn it's also bounded, because if you have a random variable which is bounded, the conditional expectation, it's bounded. So these variables xn are bounded. So they are uniformly bounded in L2, and I can apply the exercise I presented last class and today. What did we prove last time? Well, we proved that this sequence converges in L2. Okay. So I know that xn, it's converging in L2. Okay, I'm not sure if it's x, so let's call it y. Okay, so by the exercise of that I proved at the end of last class, I know that it converges in L2. So let's call y the limit in L2, and what I claim is that y it's equal to x. Okay, so let's prove that y is equal to f. Let me take a set A in Fn, and I claim that x and y, the integral over A of these random variables, is the same. Well, why is that? Because we have already seen that since my martingale is defined in this way, okay, so xn is the conditional expectation, and since A belongs to Fn, so this is equal to A xn dp. On the other hand, since xn is converging to y in L2, this is the limit in k of A xk dp. Okay, this is what I discussed at the beginning of this class, right? So they are converging in L2, so they are weakly converging, so this integral converge, and this sequence is constant after k. And it's exactly equal to that. So we proved that x and y are equal on Fn. Okay. If they are equal on Fn by a monotonic class, and this is true for all Fn, that will be true for the sigma algebra generated by Fn. But by my assumption, the sigma algebra generated by Fn, it's F. So actually, I can extend this identity to all sets A in F. And therefore, these two random variables, which are F measurable, are equal, because they integrated over the same set. So x is equal to y, as I claimed. Okay? So, what did we prove up to now? Well, we proved that xn is converging to x in L2. And since for bounded, we have seen that x and xn are bounded random variables, for bounded random variables converging, these spaces LP are all equivalent, which means that xn converges to x in LP. Okay, so we proved the theorem in the case in which x it's bounded. Now I want to extend that to x in LP. Questions up to now? So the first part of the proof, it's assume x it's bounded and prove the theorem. This is what we did. Now the second part, it's to extend that to any x in LP. So step 2 of the proof. Extend to x in LP. So what you do? Well, you approximate x by a sequence of bounded random variables. So let me take a function like that. Let me call that phi of a, and let me define xa to be phi a of x, which is bounded. Okay. Now, I know that if I define xan by xa given fn, I know
What is phi of a?
this function.
Yeah.
Function which is identity between minus a, and then constant outside. Okay, so I want phi of ax to converge to x and to be bounded. So you choose your favorite function. Okay, so here is the identity, and outside it's constant. So I define xa in this way. Xa, it's a bounded random variable. I define the martingale associated to xa, and what I know is that xan converge to xa in LP by part 1. And what I want is to estimate xn minus x in LP. Okay. So what you do, triangle inequality, and you, let's say you fix an epsilon positive, x belongs to LP, right? xa belongs to LP and it's converging to x in LP. You agree? This means that I can find A such that xa minus x in LP, it's bounded by epsilon. And I can extend that to x and A. Right? By Holder inequality, by linearity of the conditional expectation, I can write that as the conditional expectation of xa minus x given fn, and then use Holder inequality for, so let me put Holder inequality for the conditional expectation to say that this is less or equal and this is equal to the expectation of xa minus x to the power p, which is bounded by epsilon if A is larger, if A is that A or larger. Okay, so I have a control not only on xa minus x, but also on xn minus xna. Yeah.
Was that holders or adjacent?
Holder. We can use Holder. But Jensen is fine too. But okay, questions up to now? And now I can go to the triangle inequality. So I want to estimate xn minus xp. I'll say that this is bounded by xn minus xna p plus xna minus xa. Right, triangle inequality. So I fixed this epsilon. I obtained this a0, starting from which this is bounded by epsilon, but we proved that if this is bounded by epsilon, then this one is also bounded by epsilon, right? This is just what I proved. So these two are bounded by 2 epsilon, and then I still have xa and minus xa. Okay. But now I can use the result for, because xa is bounded, I can use the result for bounded random variables and say that when n converges to plus infinity, for that fixed epsilon, this goes to 0. Okay. So that limit is bounded by 2 epsilon for any epsilon. Therefore, it's 0. And that proves the theorem. Okay? Questions? So these variables, this type of martingale, for any p larger or equal than 1, you have a strong convergence. You converge in LP. Fine. Okay. So a natural question is when this is true. Given a martingale, when can I write it as the conditional expectation with respect to a variable in LP? So suppose that this is true. So suppose that this identity holds for some x in LP. Then what's clear is that if I take xn to the power p, so p it's always larger or equal than 1, so this is the conditional expectation, and by Holder or Jensen this is bounded by the expectation of xp. Okay. So if this happens, this means that this martingale is uniformly bounded in LP. Okay, the supremum over n of this expression is bounded. Okay. So if I want to prove such a theorem, at least I need to impose this condition, that it's uniformly bounded in LP. And we will see that actually this is sufficient for p larger than 1. For p equal to 1, we have the counterexample which I mentioned last class. Okay, so let's assume that p is larger than 1. Let's assume that the supremum over n of the expectation xn to the power p is bounded. Then I claim that there exists x in LP such that xn is equal to that. Right? And here it's important that p is larger than 1. Clear? So let's prove it. Well, the first question is to construct x. Okay. I have to construct this x. I have only this martingale, and I have to find x. And the way you find x, it's exactly, well, this is the condition. In order to get a weakly convergence subsequence, you just need bound in LP for p larger than 1. Okay, if you have a sequence which is bounded in LP, you can extract from that sequence a subsequence which converge weakly. Okay. Okay, if you remember, you take f in gk, xnf, it's a bounded sequence, so you can extract a subsequence which converge. You do that for a dense family, a countable family of functions f, so you have convergence for all these f's, and then you extend that for all f. Therefore you have, by approximating any f with this dense countable family. Okay? So this is a way in which you prove that if the sup in n of this x and p is finite, then there exists x in LP and a subsequence x n prime such that x n prime converge weakly to x in LP. And this is not true in L1. Okay? In L1, if you wish to find a converging subsequence, you need uniform integrability. So if for p equal to 1, if you replace that condition by the condition that xn is uniform integrable, then you have exactly the same theorem with the same proof. So I already have x, which is the weak limit of this sequence. And now I need to prove that actually xn, so my claim now and what we will do is we'll exactly use the same argument by remembering that the indicator of a set belongs to LQ. So I want to prove this identity. In order to prove that, I have to check that xn is fn measurable, okay? But this is by assumption, and then that they integrated equally in the set fn. So let's take a in fn, and I want to prove that ax dp is equal to a xn dp. Right? But now the indicator of A belongs to LQ, where Q it's related to P by this relation. So since it belongs to LQ and xn prime converge weakly to x, xn prime dp converge to x dp. And here again, as xn it's a martingale, this sequence is constant for n prime larger than n. Okay, so we have this identity, and we just prove that this happens. All right? Questions? And as I said, if you want to prove, if you want to take p equal to 1, you have to assume that xn is uniform integrable. Okay, if you know that xn is uniform integrable, you know that xn it's weakly compact in L1, so that it exists you can find a subsequence which converge in L1, and you just repeat the proof. And this is also a necessary condition, because if x belongs to L1, and if we define xn by this identity, then xn is uniform integrable.
Why did you need to find out that the identity of A belongs to L1?
Well, just to pass to the limit, because I know that this guy converged weakly to this guy, which means that if I take any function in LQ, then the product converge, the integral of the product converge. Okay, here I only know that xn prime converge weakly in LP. So, questions about the proof of this theorem? Second question. Question about what I said about p equal to 1. So p equal to 1, I claim two different things. First, that if x belongs to L1, and I defined xn by this equation, then this is a uniform integrable family. On the other hand, if xn is a uniform integrable family, I can find, okay, there is a theorem that tells you, you probably haven't seen it, but it exists, that you can find a subsequence which converge weakly in L1. And then I can repeat exactly the same proof to get that, to construct this x in L1 and to prove that you have convergence.
I know what convergence in LP is, but what's weakly convergent?
Okay, so I mean, well, I would say that xn converge weakly to x in LP if for any, so you take the dual space of LP, which is LQ, for Q given by that, and this means that xn f converge to x f for any f in LQ. So, and this is, so I'm taking xn as a linear function over LQ, which in our case is just a product. Okay, questions? Fine. And so the last theorem about convergence is to extend this LP convergence to almost sure convergence. Okay, so let now assume that xn it's the sequence where x is in LP, p larger or equal to 1. We have seen that you have convergence in LP, and now what I claim is that you have convergence almost surely. Right, so for these martingales, you have LP convergence and almost sure convergence.
And you are further assuming that the LP norms are bounded in the sample plot.
Well, they are bounded because I'm assuming that x belongs to LP, and then for by Holder I have it. questions about the statement? Okay, and the proof, it's quite pretty. So first I will observe that if x is in LP, it's in L1. So I can just assume that x belongs to L1. If x belongs to LP, it belongs to L1. So I'll assume only that x belongs to L1, and I'll prove that this sequence converge, almost surely. And how we will prove that? Well, let me define by A the set of random variables in L1 for which this property holds. For which we have convergence. And what we'll do, we'll prove that this space is linear, is dense, and it's closed. And if you have a linear space which is dense and closed in L1, it's equal to L1. All right? There are many things you have to learn. Okay. So, well, linear, it's obvious. If you have x and y in A, so you know that xn, so this martingale that you construct in this way converge almost surely. You do the same for yn, you take the sum, it also converges. So linearity, it's okay, it's easy. Now, how do you prove that it's dense? Huh? How you prove that if x is a simple function, you have almost sure convergence?
I guess. You have for L infinity, right?
Sorry?
Do you have the theorem for L infinity?
How you prove that if x is L infinity, I have almost sure convergence?
We're assuming x is the sigma algebra generated by the f.
Yeah, so x is f measurable, yes.
We can use the fact that this simple function are dense.
Yes, that I agree. The simple functions are dense, but why the property holds for the simple functions? Why star holds? I mean,
It's a set is f measurable, then it can be approximated by like unions of sets that are f n.
yeah, that I agree, but I need that this property holds. So, okay, so if I take x to be whatever, so maybe simple, I agree that this set, it's dense. But why is this set included in A?
You take an indicator function.
Yes.
It can be approximated by.
So what I have to prove is that take the indicator function, define this object, why this object is converging to x almost surely. But I don't have almost sure convergence. This is what I want to prove.
Oh, yeah, of course.
I have L1 convergence, but I don't have almost sure convergence. Any other proposal?
We can take instead that we have L1 convergence for the
Sorry?
L1 convergence for the indicator function.
Okay, so I know that this variable converges in L1.
L1 convergence.
Actually, I have that for any x. So the fact that I'm taking the indicator doesn't help.
Take L1 convergence implies convergence probability. So we can take a subsequence which can.
Subsequence, but I don't.
But that holds for every subsequence.
No. You're. Okay, so let's do the following. Let's take z in Fn. So z in L1 and measurable with respect to Fn. Okay. Now I claim that z belongs to A. Why is that so? Because if I take zk to be the conditional expectation of z given fk, since z belongs to Fn, after n, zk is equal to zn. And therefore zk converge almost surely to z. You agree with that? Okay. And then I claim that the family of, so the family Z which belongs to L1 such that Z belongs to Fn, this is dense in L1. And we proved that. The first theorem tells us exactly that, right? You take Z in L1, you have to take Y in L1. I want to approximate it by a sequence in this set. I just take the martingale defined by Y. So let's say Y n equal to the conditional expectation of y given fn, okay, we proved that this converged to y in L1. And therefore, the set is dense because I found a sequence which is converging in L1. So it's dense in L1. So this proves the second property. A, it's indeed dense. Right? Questions? So it remains to prove that A is closed. So let's take a family Y, P in A, and YP converging, no, if I want Y, okay, so I take a family XP in A. I assume that this family XP is converging to some X in L1, and what I need to prove is that X belongs to A. Okay, X belongs to A means that if I define the martingale Xn, that this sequence is converging to X almost surely. Okay. Questions? Okay, this is what I need to prove. Fine? Okay, so here is an observation. Let's use Doob's inequality. Let's see that Doob's inequality, it's really strong. So I have X in L1. X, it's the limit, and I defined the martingale associated to X. And what Doob's inequality tells me is that the max g less than n of x g larger than lambda, this is bounded by 1 over lambda xn. This is Doob. But xn is the conditional expectation of x. So this is also bounded by 1 over lambda, the expectation of x. Now the right-hand side doesn't depend on n. So I can send n to infinity to conclude that the probability that the soup of xj to be larger than lambda, it's bounded by that. Okay. And if I send lambda to infinity, the right hand side converges to 0. This means that this random variable here, it's finite almost surely. Right? The probability that it's infinite is 0. So if I have a martingale, which is defined through this conditional expectation, then the supremum over all possible values, over all times, it's finite. Pretty strong. Okay, you agree with that? Okay, this is true for any lambda. So the probability, let me call A or B the set in which the supremum is plus infinity. The probability of B, it's bounded by that for any lambda, which is bounded by that. And if I take lambda to infinity, this is 0.
O supremo do módulo do XJ é mensurável.
Well, if I take random variables which are measurable, so all these ones are measurable with respect to f. And if you take the supremum of a family which is f measurable, it's f measurable. Okay, any sequence, increasing sequence of functions is measurable. Okay, so now I know that this sequence xj, it's bounded. If it's bounded, and if I want to show that it converges, it's enough to show that the limit sup is equal to the limit inf. So what I need to prove is that the limit sup of xj, it's equal to the limit inf. I can repeat the same computation I just did, but instead of looking at xj, I'll take the difference between xj and xpj. Okay, so let me define xpj. So xp, okay, it's these variables which belongs to A. So I know that for them I have the convergence, the almost sure convergence. Okay. I want to prove that X kept this property. So if I define xp given fj, this martingale, I know that this martingale is converging almost surely to xp for all p. And I just repeat the computation I did before to get that the probability that the supremum for j. So now in this computation I know that this is a martingale. So if I take the difference, xj minus xjp, this is also a martingale. Difference of two martingales is a martingale. So I can repeat exactly the same computation. Right? But now I know that xp is converging in L1 to x. Okay, I have this family xp, they belong to A, and they are converging in L1 to some x. So the right-hand side, as p converges to plus infinity, is going to 0. Okay? So this means that if I take lambda small, for any lambda, this random variable, as p goes to infinity, it's converging to 0 in probability. Okay? So I know that this random variable, which is the supremum over j of xj minus xjp, that this is going to 0 in probability as p goes to infinity. So they're pretty close. Because now, since it's going to 0 in probability for p, I can take a subsequence in which it goes to 0 almost surely. So this supremum for a subsequence p prime, it's converging to 0 almost surely. And then it's done. Because, well, you know that these guys are converging almost surely. And the difference, it's converging to 0 almost surely. So they are converging almost surely. So let me write that more precisely. Okay, let me write it here. So this is converging to 0. You all agree with that? So I can extract a subsequence which converge almost surely. Fine, and this is what I want to prove. So what I do, I want to prove that these two limits are equal. So let's take that the limit sup, I want to show that these two limits are equal. They are larger or equal to 0, so I need an upper bound. So let's add and I do the same thing for the limit inf. Okay, I'll have to erase. I have that. I know that x p prime j behaves well, and that this difference behaves well. So it's very natural to just subtract and add. Okay. Now, the limit sup of a sum, it's bounded by the sum of the limit sup. minus. And for the limitive, it's just the opposite, but I have the minus sign. Okay. These two quantities are equal because xp belongs to my set A. Right? I started from xp, the family in A, which was converging to x in L1. So for each p, I know that the martingale converge almost surely. So the limit sup is equal to the limit inf. So these two cancel, and what remains are these two. But these two, I can bound that by the supremum. So this is bounded by twice the supremum over j of xj minus xj prime. And this is going to 0 because we just proved that if I take that sequence, this is converging almost surely to 0. And so A, it's closed in L1, and therefore A equals to L1. And that completes the proof. Questions?
I'm a little bit confused about how you did the order of the limits there.
Of what?
The order of the limits. So you first took the limit in j.
I need to take the limit in j. And so when I take the limit in j, these two are equal. Then these two remain. And I replace the limit in j by the supremum in j. Okay, now I have a function of p prime. But I proved that this sequence in p prime converge to 0 almost surely. Okay, so this was my, this is what's written here. So I have something 0 at the beginning. 0, it's less than the supreme.
Should it be like lim sup of there? Lim sup of that?
No, here p prime it's fixed.
Yeah.
So I have a sup in j and I have this. So I have this quantity which doesn't depend on p, which is positive, and it's bounded by this quantity. And this is true for any p prime. Now I can send p prime to infinity, and this goes to 0, almost surely. I have two variables which are positive, whose difference is positive, and which is bounded by that. And this is going to 0 almost surely, so this variable is equal to 0 almost surely. Any other question? So these are the three basic convergence theorems. We will see at the end of this section, or the chapter on martingales, another convergence theorem. But these are the basic ones. Questions? Okay, so if not, we end here and we continue on Tuesday with Doob decomposition of submartingales.
Professor, da aplicação do
Algum dia.